Okay, so we've talked in Gen Chem about limiting reactants or limiting reagents. And you know that one of your reagents is going to be the thing that you run out of first. And that's absolutely true, but that doesn't mean that you're necessarily ready to go into literature, figure out what it is that you need, and go into the lab and make it. So there's a little bit of math that we have to do, and it's based on all the principles that you already know, but I want to make sure that you know how to adapt from one thing to another, right? So you may have a reaction where you're starting with A, whatever A is, and B, they're combining to make D. You have some form of solvent present, and you may have C, which C could be a catalyst or an acid or a base or whatever it may be. Well, the thing is that probably D is going to be dictated by either A or B or both. Maybe you're combining the two. And it may be that you're thinking, okay, well, you're going to need a little bit extra of one thing than the other. So you just go to the lab and you start throwing things together. Well, that's not the way we do things. We say that you don't want to reinvent the wheel. What you want to do instead is look at what somebody else did in the literature and try to adapt what they used. Because in some cases, it may be that 1 of A and 1.3 of B, totally fine. But how much C do you add? And what I mean by 1 to 1.3 is I'm talking about the molar ratio. So for every 1 mole of A, it may be that you need 1.3 moles of B. But if C is a catalyst, how much do you add? You don't know. How much solvent do you use? Well, there's a general type of rule with that, but what solvent do you use or what's the best for this reaction? Now, a lot of times when we do research, we do not have an exact measure of what we're doing. So we don't have A and we don't have B. So we tend to find things that are similar and start where somebody else sort of left off. And if that doesn't work, we look for some other type of reaction that they use. But in either case, you need to be able to take what is given to you in literature, adapt that to what you're doing, figure out what these molar ratios are here, right? Like that is key, and then be able to scale it to any level that you want to do it in. Here's what I mean by the scale. So when we're talking about scaling, what we're talking about is how much of A do you start with? How much of B do you start with? It may be that literature starts with 100 grams of something. You have 2. And so you can't just divide things by the number of grams, because remember, it's not about grams, it's about moles. You may not have the same type of stock solutions that they are using. It's not about number of milliliters, it's about moles. So when we're looking for the molar ratio, that's exactly what we're looking for, the molar ratio. We're looking for the ratio of the desired products to other reactants in moles. So in moles is very important. So in theory, what we have to do when we're looking at literature is take whatever reaction we have there and convert from grams if we're given grams, liters or milliliters if we're given volume, even gas pressures, into how many moles of all these things do I have? And then we're going to divide each one of those individually by whatever it is that you want to be your limiting reactant or your desired product or whatever you mean by that. So in this case, I would say that that's A. And the reason why I say desired product rather than talking about this being the limiting reagent, well, here's what I mean by that. C could be a catalyst. If C is a catalyst, it's definitely going to be the lowest number of moles. You can do that as that's your mole number 1, that's fine. But just realize that that means that this might be, 500, and this may be 700, whatever that may be, in order to get 500D. Okay, so that's completely the numbers you're going to get if you start talking about C as your catalyst is going to be a ratio of 1. It could be thousands, tens of thousands even if you've got catalytic amounts. So generally speaking, what I try to do is I try to set it so that instead, one of these that's going into my reaction is going to be 1. And by the desired product, what I mean is I want to know how much I need to get 1, whatever this is. So 1 of a general ratio, okay? That might mean that we need to figure out something, for example. So let me erase those, and let's try instead to do this with actual numbers. And then we're going to do lots more actual numbers, okay? So let's say that you go into literature and you figure out that the literature uses 3.6 moles of A and let's say 8.6 moles of B. Meanwhile, you're only using 0.5 moles of C. And if this is a 1-to-1 relationship, you know from general chemistry that you're going to get 3.6 moles of T, right? Well, so let's look at what that means exactly. So let's look at what that could mean, okay? So what we can say is that I've got more of this than this, right? So I'm going to take that value of 8.6 moles of B for 3.6 moles of A, right? So what that's going to give me is 2.39. What that tells me is that I need 2.39 moles of B for every 1 mole of A, which means that my molar equivalence here is 2.4 approximately to 1, or 1 to 2.4, depending on which one we're talking about is which, right? Well, it's going to be much less than that when it comes to C, because C is obviously in catalytic amounts. So C would be instead, we're going to keep A the same thing that we're using down below, right? So 0.5 moles of C for every 3.6 moles of A, right? And so what you find there is that the molar ratio is 0.139 moles of C per 1 mole of A. Now, we have to compare apples to apples here. So if we say, okay, well, I have 1 mole of A in each case, then this is going to be 0.139 moles of C to 1 of A. Okay, so that's sort of how we look at these things. Now, how do you get to that point? Well, let's look at things. Let's look at things back where we might remember how to address things from general chemistry. Here's an example of a reaction that's actually quite similar to what we were just talking about. So let's say we start with this guy. And we're going to, using a catalyst, add this alcohol. Now, that alcohol could be the solvent. It could be a reactant, and you have another solvent, and you're trying to get this product. Well, the thing is that, again, you want to look in literature and say, what do you use? So we want to look at what it is that they may have available. Thing is that sometimes things are not necessarily as you expect them to be. Maybe your reactant is a liquid. So I am absolutely making up these numbers, so please know that this is not from literature. I am making this up, okay? So let's say we have 10 milliliters of ethanol. I'm going to leave the solvent question out for now because that could be that that's something else that we're going to deal with in a minute. I'm going to assume that probably our starting material here is also a liquid. But for the purposes of this exercise, I'm going to again give you some data. Let's say that instead we're starting here with 3.5 grams. Okay. Now, that's a mass. Here we've got a volume, okay? And H2SO4, let's say that we're starting with this as a solution. Let's say that we're starting with this as a 3 molar solution, and we add 0.1 milliliters. So the question may be, how much of this can we make? And then the other question may be, if you go into the lab and you instead, your desire or your goal is to use 20 grams of this starting material, because that's what you have. How do we scale that up? Well, so the first thing that's very important for you to realize is that this goal you need to deal with after you have your ratios. So for now, I'm going to put that on hold, okay? So deal with that later. But I go back to a chart that we've probably looked at least if you have me or you reviewed limiting reagents, which certainly I would say to go back and look at. We did this in Gen Chem. So remember, whenever you're going from whatever it is that you need to get to figure out what it is that you're going to make in the end, we look at things one thing at a time. So we can go from grams of A, in this case, this would be A, and we're trying to get to grams of B, so that's our product. So grams of A, we have to figure out the moles of A, moles of B, and we get to grams of B. We could do the same thing from volume. So the thing is that, okay, this time it's not A. This time it's X. It's fine. So this would be X. And then we still try to get to the volume or the grams of B. We can go from different locations on this chart into what you're finally getting. But the point is that you have to go through a mole-to-mole conversion. Well, in this case, it's all a 1-to-1. That certainly helps, right? But the first thing we need to do is take this, convert it to 2 moles. Take this, convert it to moles. Take this, convert that to moles. And then look at our ratios, where our ratio is per ratio of what we have to A, okay? So let me show you an example of that. So 3.5 grams of methyl cyclohexane. We need to figure out how many moles we have. So I look up the molar mass, figure it out, right? And that is 96.2 grams per mole. Remember, grams needs to cancel. So we cancel those out, and that's going to tell us how many moles we have. So real quick, I get that is 0.0364 moles of our methyl-cyclohexene. Okay, now we need to do the same thing for ethanol. So if I have 10 milliliters of ethanol, okay, I'm starting with milliliters. When you're starting with a volume of something that's pure, we need a key thing to figure out what we have. You may or may not realize or remember this, but density is how we do that. Remember, we go from milliliters to grams, and then we're going to go from grams to moles. So let's look up that density. Okay, that is 0.79 grams per milliliter. Okay. Now we need the molar mass of ethanol, which is 46 point, let's call it 1 gram per mole. Why did I put grams on the bottom? Remember, that has to cancel out. So milliliters cancel, grams cancel, right? Now that's going to tell us how many moles we have of this as well. So let's do a quick calculation. Okay, I get 1 moles of ethanol. Hey, good. That's what we should have because this should probably be our limiting reagent, right? Okay, the third thing we have here is we have to deal with the H2SO3. So I'm sorry, I'm going to have to shrink this down one more time if I can. There we go. So it says that we have 0.1 milliliter of a 3 molar solution. Well, I love solutions like this. Let me show you why. Remember, we've got 0.1 milliliter. Now, you could probably convert that to liters in your head, but just so that we all remember how to do this, there's 1,000 milliliters per liter. But here's the wonderful thing about molarity. Okay, we have a 3 molar solution, so that means that we have 3 moles for every 1 liter. There's no looking up density. There's no figuring out how many grams per mil you have. It's just a nice straight answer at this point. So that will give us 3 times 10 to the negative 4 moles, or 0.0003 moles. Okay, now we need to figure out our ratios. So I'm going to move this down. Here we go. So what we're going to do is we're going to compare everything to this. Okay, so that's the goal. That's what we're trying to figure out. So figuring out our molar ratio is real simple. So we take 0.171 moles of ethanol is what we have for every 0.0364 moles of methylcyclohexane, or ene, sorry. That gives us a ratio of 4.7, give or take, to 1, right? So that's 4.7 moles of ethanol to 1 mole of this guy, okay? Let's now do the same thing for our H2SO4. We have 0.0003 moles of H2SO4 for every 0.0364 moles of methylcyclohexane. That gives us a ratio of 0.008, give or take, moles of H2SO4 to 1 mole of ethylcyclohexene. Okay, so now we have our molar ratios. This is what we just did all that work for, right there, okay? You might say, well, what's the point of that? Okay, now, do you remember how we put aside some information earlier? We said that we wanted to go into the lab and start with, for ourselves, 20 grams of methylcyclohexene. Well, here's how we figure that out now. If we have 20 grams of methylcyclohexene, remember, that's 96.2 grams per mole. So we've got 96.2 grams per mole. That tells me that I need 20 divided by 96.2 is we're using 0.208 moles of ethylcyclohexene. Well, look, I can figure out really easily now how much ethanol I need because I need 0.208 moles times 4.7 moles of ethanol. That's going to give me 0.977 moles of ethanol. And that's how much I need. Now, do I still have to figure out and go back and convert the moles then to milliliters again? Yes, I do. But this is how we do this, okay? So now I'm going to say, well, I'm going to start with 0.208 moles of ethanol, and I need this much H2SO4. That's going to give me 0.208 times 0.008. I'm going to need 0.0017 moles of H2SO4. And to get back to where we started with how many milliliters do you need or how many of this or that do you need, you just have to go backwards with the same type of thing we were doing. Now, the next thing is that I want to just make sure that we're all on par with, right, is that sometimes you get some reagents that are percentage types of things. So what you might see is this is 15% of whatever it may be. 15% solution of NaOH, for example. The issue here is that looking at that right now, I can't tell you whether or not that is a mass or a mass volume type of solution. Well, here's the thing. Most of the time you could look it up and go, what's more common? And go from there. But most of the time when we're dealing with stuff, generally speaking, it's mass volume. So let's just assume for a minute that we've got a 15% mass volume. It's more common to have a mass volume. What that's telling me is that I have 15 grams of whatever that solute is per every 100 milliliters. So remember, 15% is the same thing as saying 15 parts of the whole. And so when it comes to mass volume, we define the part as in grams, and most of the time the volume is in milliliters. So that's sort of the definition of mass volume. So you can go from here and multiply by, let's say you're using 75 milliliters, and that'll get you, multiply, and that'll get you the number of grams that you have. You can go from grams to moles using the molar mass, just like you would otherwise. Okay, so you can just keep going there, right? And I'm sure that you all can figure that out now. The other thing I want to make sure that we review really quickly is that of how to dilute a solution. So remember, it's C1V1 is equal to C2V2. So let's say that we start with a 25% solution of something, and we want to take that down to a 5% solution. Well, I could say that I have a 0.25 is my C1. I need to use an unknown volume of that in order to get me to a new concentration of 0.05, so that's 5%, right? And let's say you wanted 100 mils of that, so whatever that new volume is. You would then solve for V1. So V1 would be equal to 0.05 times 100 divided by 0.25. V1 is going to tell you the amount of this 0.25 solution that you need to put into a 100 milliliter volumetric flask, fill to the line with solvent in order to give you a 5% solution of whatever that is. Just making sure we remember how to do that. I hope this has been helpful. I hope that you have a lot of answers or questions answered at this point. Good luck. Hope it goes well. Thanks.